Hello and welcome back to the Science of Concrete Materials class. This is lecture number 5. This lecture's topic is the composition of Portland cement. Okay, so far we have understood how the Portland cement idea developed over time, and we have gone over how modern Portland cement is manufactured, and what products referred to as phases are formed. Now we need to go over the Portland cement composition, and then after that the Portland cement types, of course. Just remember, as I said before, the Portland name is really a generic name, and it is given to cement with certain characteristics that meets certain criteria. That is the ASTM C150. As mentioned before, the cement is the active component that reacts with water and creates the binder, which is the paste, within the concrete matrix, and responsible for the strength gain over time. However, not all phases present in the cement as a result of the manufacturing process contribute equally to the desired properties of concrete. Actually, some of the phases do not actually contribute at all, and some may have negative effect in certain conditions. This is, of course, due to the nature of the chemistry and morphology of these phases or compounds. So let's go over each major phase and see what they do. This slide here shows the major compounds or phases of the Portland cement and the range of percentage of the overall composition. As you see, the major phases are the tricalcium silicate, referred to in shorthand notation as C₃S, or it has other names depending on the impurities present within the phase, referred to as A-light. It's, as I said, the composition between 50 to 70%. Dicalcium silicate, C₂S, or referred to as the impure phases as the B-light. It's about 15 to 30%. Tricalcium aluminate, C₃A, about 5 to 10%. The tetracalcium aluminoferrite, C₄AF, 5 to 15%. And of course, the gypsum we add to the clinker, calcium sulfate dihydrate mostly, and referred to shorthand notation C₃S bar H2, roughly around 5%. Of course, in addition, as we mentioned before, there are minor phases and oxides. We will cover them later. So let's see how every phase contribute. Let's first reiterate a couple of points. The cement reaction with water is an exothermic reaction, means it gives off heat. The reaction of calcium silicates phases with water is what produces the calcium silicate hydrate gel, which is responsible for the strength. These two phases, C₃S and C₂S. As I said, the C₃S, roughly around 50% or 50-70. It's very reactive compound, gives high heat of hydration, and responsible for the early strength. It gives high early strength. The C₂S, average of 25%. This one, lower heat of hydration, slow reaction, and responsible for the later strength gain. The C₃A, this compound is very reactive. If not controlled, will cause flash set. It generates, high early heat and causes problem with the sulfate attack, as we will see later. The C₄AF, and as I mentioned before, not much known about this phase and its contribution. We will study its hydration when we in the lecture of the cement hydration. The gypsum, which I said about 5%. This one is used to control the set of cement. It reacts with C₃A to prevent the flash set to allow for mixing and handling of the concrete eventually. So it is really logical, knowing the contribution of all these phases, to assume that relative quantities of these phases will affect the properties of the hydration products, the cement pastes and the concrete. As follows: the relative quantities of these phases will affect the setting time. As I mentioned, if the C₃A, for example, sets very quickly, the percentage of C₃S will impact the early strength gain. So setting time is impacted, the rate of strength development, the overall strength, durability, and again, just keep in mind the C₃A and its relation to the sulfate attack, and the color. So it is important then to know the chemical composition of the cement. So in addition to knowing the cement composition, we have to perform several tests on the cement so that we can predict its behavior and in its intended function. For the composition, the intent is to know the compound, the phase compositions, based upon which we will predict the behavior of the cement. Also knowing the overall chemical analysis and setting certain chemical limits based on the required behavior. Okay? The routine chemical analysis of the cement is reported using the oxides of the elements present within the cement or the clinker, usually reported in shorthand notation, as we have seen earlier. Since properties of the Portland cement are related to the compound composition, these are the oxides that you get from typical analysis. We will talk about this nowadays. Certain methodologies exist to directly determine the composition based on the compound, but typically the typical process was based on the oxide analysis. The oxide analysis, from them we will calculate these compound analysis. So I said, since the properties of Portland cement are related to the compound composition, it is difficult to draw any conclusions from the cement oxide analysis, such the ones are shown here. So it is common practice in the cement industry to compute the compound composition of Portland cement from the oxide analysis by using a set of equations which were originally developed by Mr. Bogue long ago, and they still work. But again, eventually, the intent is to know the compound composition shown here. So, as I said, the typical or the routine analysis involves the determination of the oxide analysis and then the compound. But, more accurate methodology, as I said, exists, as direct determination of the compound composition, such as the XRD, the X-ray diffraction methodology, which I used extensively during my research, and also the reflected light microscopy, as you see in this micrograph here. Basically, it's performed on polished and etched sample with certain chemical compounds to reveal some of the phases. These, the two methods, commonly used for direct quantitative analysis of Portland cement clinker. The first method involves, as I said, the reflected light microscopy for the polished and etched sample. Is followed by a point count. of areas occupied by the various compounds. Typically after etching with certain compound, the C₃S, appear as hexagonal plate crystals. The C₂S appears, as rounded grains, and within them, twinning bands of C₃A and C₄AF, as interstitial phases. Sorry, let me go back here. This stuff you see here. The second methodology which involves, this one, is applicable to pulverized cements. Cements ground to a certain fineness. This involves the X-ray diffraction, and this is the result of an X-ray diffraction. Okay, sorry, let me go back. Okay, X-ray diffraction of powder specimens. Usually calibration curves, based on known mixtures of pure compounds, and an internal standard are required. An estimate of the compound is made by using these curves and the intensity ratios between a selected diffraction peak of the compound and the internal standard is measured. The internal standard usually used is the titanium oxide, TiO2. As I said, these methods require a special skill, special equipment, special skills, and basically they are not necessary for routine quality control. But nonetheless, in research, they are used extensively, and in many cases, where I have, for example, been involved in some investigation of certain issues, like in forensic analysis, we have insisted on, for example, on X-ray diffraction methodology to determine the actual compound composition of the cement. So it's a very powerful tool, and it can be very beneficial. So back to the oxide analysis. I'm going very fast with these slides. Back to the oxide analysis, which is more commonly used, mostly on the cement mill certificates. That's what you get. This is referenced by ASTM C114, and a common methodology also used for oxide analysis is the X-ray fluorescence spectrometry, XRF, abbreviated as XRF. The instrument is shown here. Okay. Just generally, the X-ray fluorescence spectrometry is a non-destructive instrumental method of quantitative and qualitative analysis of chemical elements based on measurement of the intensities of their X-ray spectral lines emitted by secondary excitation. The primary beam, typically taken from an X-ray tube, irradiates the specimen, exciting each chemical element to emit a secondary spectral lines, which have a wavelength characteristic of that element and intensities related to its concentration. The secondary radiation is analyzed by means of a crystal rotated in the plane of radiation, and its intensity measured using a detector. This is the type of intensity graphs you get from an XRF analysis. Here we show the result of a typical oxide analysis of a cement. As we see here, the major oxides and minor oxides right here. These are the major oxides, some minor elements, present right here. Other minor components are shown, as I said, and are reported through separate determinations typically. But are reported on the cement mill certificate. So when you get a cement mill certificate, you will get all this information. This is, again, ASTM C114, the standard methods of chemical analysis of hydraulic cement. The typical method or the XRF. And this is the information you will get on a typical mill certificate, as I said. And for example, free lime, why do we care about these components? The free lime is important since its presence causes unsoundness in concrete. The same thing with the magnesium oxide. Okay? So this is it is not the calcium oxide that will be combined with silicate to form C₂S and C₃S. This is a free lime. And we will see later what is the significance of those two, the MgO and the free lime. This slide here, show the typical percentages of the major and minor components of the oxide analysis. It is important that the engineer is familiar with these elements and the specifications, on his or her job, so that the mill certificate can be reviewed carefully to match the specifications and the requirements. Okay, it is very important to be able to read the mill certificate and flag any anomalies or anything that may not comply with the specifications written for your job. As mentioned above, the equations developed by Mr. Bogue are used to calculate the cement phases, the compounds, as shown here in this slide. These are the equations, for example, to calculate the C₃S from the percentage of calcium oxide, silicon dioxide, the alumina Al2O3, the ferric oxide, and the sulfur, the SO3, C₂S. Again, you require this, which calculated here, and again the silicon dioxide, C₃A, the alumina and the ferric oxide, the C₄AF in terms of the ferric oxide. And again, these equations are valid only when the ratio between A and F above 0.64. When the ratio is less, ASTM C150 uses different set of equations. Okay, remember that. You need to refer to ASTM C150. So, okay, based on the Bogue equation, or this is the Bogue composition, from these oxide analysis percentages, we are able to calculate the C₃S. As mentioned here, C₂S, this we get 58%, 15.6, 8.5, and 8.8 for C₃A. This is what we refer to as Bogue potential composition, because the exact composition sometimes determined from direct method such as the XRD will vary. Okay, but this is very convenient, and it's a very powerful tool, actually. I mean, we have to give a lot of credit to Mr. Bogue for developing these equations, which have been used for years and years. Okay, this is the alkali content, how it's determined. As if you remember before, I mentioned about the alkali content reported as sodium equivalent, Na2OE, which is calculated as follows: the percentage of Na2O, sodium oxide, 0.15, plus 0.658 multiplied by the potassium oxide. So this is how it's reported. And again, this is significant in many cases, especially when there is a potential for alkali-silica reaction, and other issues that, as I said, like the internal sulfate attack and other stuff that is beyond the scope of this class. Okay, as I mentioned, or I've been saying, the Bogue calculations, have many limitations. The Bogue equations are, based on the following assumptions. First of all, they have certain assumptions. That all four phases are pure, which is never the case. Second, all the ferric oxide present occurs as C₄AF, and the quantities of A, the aluminum oxide, equals 0.64 times the ferric oxide, are subtracted from the appropriate totals. So the remaining Al2O3 is combined as C₃A, and a further quantity of calcium oxide, CaO, equals 1.65 times the Al2O3 is subtracted from the total remaining CaO. Then again, this also the silicon dioxide combines initially with CaO to calcium oxide to form C₂S, given a provisional figure. The calcium oxide combining with the silicon dioxide, equals to 2.87 times the SiO2, is subtracted from the total calcium oxide figure, and the remaining calcium oxide is then combined with the part of the C₂S, equals 4.07 times the CaO to form C₃S. A lot of limitations and caveats, but as I said, nonetheless, the equations are excellent approximation of the phase or compound composition of the cement, and you always have the option to go to the XRD or the reflected light microscopy for additional or added confirmation of the cement composition. So, sorry, so let me go back. I went too far. So anyway, so as we said, even small differences in oxide analysis of two cements can result in a large difference in their compound composition. This is illustrated here in these two tables, which there is a comparison of 5 cements. The oxide analysis shown in the table on the top here, and the compound composition based on Bogue is shown in this equation right here. So if a comparison between cements number 1 and 2 shows that 1% cements 1 and 2, 1% decrease in the Al2O3 content with a corresponding increase in the ferric oxide from 2.9 to 0.3. This lowered the C₃A and C₂O contents by 4.3 and 4%. See, respectively, between the C₃S and C₃A. Okay. Similarly, the comparison between cements 4 and 5 here, cements 4 and 5, shows that 1% decrease in the CaO content, calcium oxide content, okay, with a corresponding increase in the silicon dioxide content from 20.1 to 20.1. This caused the C₃S to drop by almost 11% actually, from 53.6 to 42. And the C₂S to rise almost by the same amount, from 17.2 to 28.8. Okay, so we have the moral of the story. We have to be aware of some of the assumptions, underlying the Bogue equations, and use them with care, as I said. So the Bogue equations assume that chemical reactions of formation of clinker compounds have proceeded to completion, and that the presence of impurities such as the magnesium oxide and the alkalis can be ignored, which is not true. Both assumptions are not valid. Hence in some cases the computed compound composition, especially the amounts of C₃A and C₄AF in cement, are known to deviate considerably from the actual compound composition determined by direct methods. This is why the computed compound composition by the Bogue equations is referred to as the potential compound composition. Potential, not true 100%. Okay, so because properties of Portland cements are influenced by the proportion and the type of compound present, the Bogue equations serve a useful purpose by offering an easy method of providing first estimate of the compound composition of the Portland cement from oxide analysis. As a result, though, Bogue composition may be off by as much as 10% compared to the XRD determined compositions. The quantitative XRD is more accurate in determining the phase composition. However, as mentioned earlier, it requires special instruments and vast and thorough knowledge of the crystal structure and the chemistry of potential phases present in the clinker. So that you have to know. Of course, you have to create a library of the potential crystal structures to the potential compounds that you believe are present in the clinker or the cement you are analyzing. So just let me elaborate a bit more. Let me go back here a bit. So just a few more words about the XRD method. Max von Loo in 1912, discovered that crystalline substances act as three-dimensional diffraction gratings for X-ray wavelengths, similar, to the spacing of planes in a crystal lattice. You need to review the material science class here a bit. The X-ray diffraction is now a common technique for the study of a crystal structure and atomic spacing. As I said, very powerful tool. The X-ray diffraction is based on constructive interference, of monochromatic X-rays and a crystalline sample. These X-rays are generated by a cathode ray tube, filtered to produce monochromatic radiation, collimated to concentrate and directed toward the sample. In our case, the sample usually cement that is ground to a certain fineness. The interaction of the incident rays with the sample produces constructive interference, and a diffracted ray. When the condition satisfies, Bragg's law, which is, relates the wavelength of the electromagnetic radiation to the diffraction angle. Remember this theta. Diffraction angle and the lattice spacing in a crystalline sample. These diffracted X-ray rays are then detected and processed and counted. So by scanning the sample through a range of these two theta angles based on a certain range that will cover basically the phases or compounds believed to be present in this sample you are analyzing, which you are dealing with cement. So as I said, through knowledge, experience, and research, you would have created a library of what are the phases and the compounds typically present in your samples. Okay, by scanning the sample through a range of 2 theta angles, all possible diffraction directions of the lattice should be attained due to the random orientation of this powdered sample or material. Conversion of the diffraction peaks, these, to the D spacings allow identification of the mineral. So basically, again, there is a library you created. So these diffraction peaks are converted to the D spacing. After that, the minerals are identified because each mineral has a set of unique D spacings. Typically, this is achieved by comparison of D spacing with standard reference patterns. Okay. So basically, you get a graph similar to this. This is the result of an XRD analysis using some quantification method. As I said, the internal standard method, where you have some internal standard you mix with your sample, typically titanium oxide, and then will serve as a reference to compare the peaks. You get the relative quantities of each of these phases. Or there is another method called the Rietveld method. That's also a very powerful method, but again requires experience and knowledge. So then by one of these two methods, the phase composition can be directly determined. And as I said, if it's done with skill and care and knowledge, it gives good results as compared to both. Okay, so let me just mention a few points worth mentioning here about the phases of the Portland cement. The hydration rate and the nature of the hydration products are influenced by the following points to a certain extent. First of all, the cement composition, of course, percent by weight, crystal structure, and again, it's beyond this class to go over the crystal structure, but the crystal structure of the compounds, for example, the C₃S might be present, or the C₃A, in various different crystal structures. It affects its properties. The inclusions of other elements within the cement phases. For example, these phases are never, as I said, present in the pure form without any inclusions. For example, C₃S, for C₃S, the impure phase is A light, as I mentioned earlier. For C₂S, the impure phase is a common phase called the beta B light. And other phases, of course, have the same. The presence of the magnesium oxide, MgO, and the uncombined calcium oxide, referred to as the free line, if you remember. Okay. When present in crystalline form, not in amorphous form, they are less reactive, and this slow hydration will result in expansive product after the concrete has hardened, referred to as unsoundness. We will cover it. Again, also the rate of reaction and strength gain are also influenced by the fineness of the cement. Usually this is reported by meter square per kilogram. Higher fineness means faster hydration and strength gain. For a given compound composition, same compound composition, the rate of reactivity and, of course, the strength development can be enhanced by finer grinding of the cement. However, the cost of grinding and the heat evolved on hydration set some limits on this fineness. This one, of course, we will go over. For quality control purposes, though, in the cement industry, the fineness is easily determined as the residue on standard sieves, such as the number 200 mesh, the 75 micron, or the number 325, which is the 45 micron. It is generally agreed that cement particles larger than 45 micron are slow to hydrate, and those larger than 75 may never hydrate completely. So particle size distribution is important. However, though, an estimate of the relative rates of reactivity of cements with similar compound compositions cannot be made without, as I just mentioned, knowing the complete particle size distribution. So as the determination of the particle size distribution is either cumbersome or requires, extensive or expensive equipment, it is a common practice in the industry to obtain a relative measure of the particle size distribution from surface area analysis of the cement using the plane air permeability method, ASTM C₂04. We will go over. Okay, these few points I just wanted to mention here. Of course, everything I mentioned here we will go over one way or another in the coming up lectures. Okay, so by this we have finished the cement composition lecture. Thank you for watching, and I will see you next time. Next lecture we will talk about the types of Portland cements. Okay, thank you.